Okay, so welcome back. Like I mentioned, today's plan is to cover triple integrals and cylindrical and spherical coordinates, the analog to double integrals and polar coordinates that we saw earlier in chapter 15. Okay, so let's think back to double integrals and polar coordinates, and we're going to just quickly remember a couple of details and work through a bit of the derivation, because that'll give us, I think, a nice jumping off point for the next topics. So recall that if we have a double integral over some domain of some integrand f of xy dA, a double integral, we can, of course, write that in terms of rectangular coordinates x and y, like this. Y goes from some function of x to another function of x, and x goes from a to b, dy dx. And of course, we could write it the other way too, with y on the outside and x on the inside. Sometimes it's beneficial to do it that way. Sometimes it's better to do it this way. But also we can convert the polar coordinates. Sometimes we do this because the integrand kind of makes it nicer for us to convert to polar coordinates. Sometimes because the domain of integration is nicer to describe in polar coordinates, sometimes for both reasons at the same time. And the integral overall looks kind of qualitatively similar to the x and y integral, except for the kind of one big difference we get in r dr d theta. And where did that r come from? So let's consider a polar, quote, rectangle, where we're going from some radius, say r naught, to some radius, say r1, and we're going from angle theta naught to angle theta 1. In other words, we are traversing an angle, delta theta, and a radius delta r. And that gives us this, we might call it something like a polar rectangle, a slice of an annulus, a slice of a donut, like this. Why is this a polar rectangle? Why do we call it a rectangle, even though it's not really a rectangle? That's because we can describe it in kind of a rectangular fashion, where r and theta are completely independent of one another. Theta sweeps out from theta naught to theta 1 independent of where r is, and r goes from r naught to r1 independent of which theta we're dealing with. So this is like the region r naught comma r1 cross theta naught comma theta 1 in polar coordinates. So that's why we kind of call it a polar rectangle, because it feels a bit like a rectangle. And the important thing to notice here is that even for the same delta r, if my initial radius r naught is very large, this sweeps out a larger area than if my radius r naught was very small. If I'm close to the origin, a 10 degree or whatever delta theta sweeps out a small area. If I'm far away from the origin, it sweeps out a larger area. So we want to account for that. And we note that for some kind of radial distance r, this circular arc here, this arc length, is actually r delta theta. And then we say, well, this polar rectangle, that's not quite a rectangle, for a small delta r and a small delta theta, it's approximately an actual rectangle, or rectangular rectangle is that. It's kind of a funny way to say it, but so this little chunk of area here, we'll call it dA, some chunk of some bigger polar domain over which we're integrating, is approximately, or oops, let me call it delta A, just to be consistent with my notation here. This delta A is approximately, well, length times width is delta R times R delta theta, and that's where this extra factor of R comes from. So again, we've seen this before, but I wanted this to be fresh in our minds because we're going to use this pretty much directly in cylindrical coordinates, and we're also going to use it in spherical coordinates. So I want this to be kind of a fresh idea. Okay, so the two big ideas, one is that when we have a dA, or this little chunk of region over which we're integrating, uh, we have to be a little bit careful, right? In rectangular coordinates, it works out pretty nicely, but in other coordinate systems, we have to just be a little careful what we actually get at the end of that integral. And the second thing is just to remember that uh, that the arc length along a circular segment is the radius times the change in angle. Those are ideas that we will use heavily coming up here. Okay, so now let's move to 3 dimensions and look at cylindrical coordinates. The super nice thing about cylindrical coordinates is it's basically the same as polar coordinates. So what's the idea of cylindrical coordinates? So suppose I have some point in 3-dimensional space. XYZ, and its height z above the point xy in the xy plane, like this. So in rectangular coordinates, we kind of start at the origin. We go x units along the x axis. We go then y units parallel to y and z units parallel to z, and we get to this 3-dimensional point. And we could describe this a different way. Instead of telling you go this far along x and then this far along y and then go up z units, I could instead tell you go an angle theta starting at the positive x-axis and rotating towards the positive y-axis in that direction, staying in the xy plane, but rotate yourself theta degrees or radians around, and then go a distance r outwards. That will take you to a point r comma theta in the xy plane. And then once we get there, we'll just go up z units. We're still going up z units above that point. So xyz turns into r comma theta comma z. So z doesn't get like polarified or whatever. Z is just the height that we go above the point r theta in that horizontal plane. But we're describing the point in the horizontal plane differently. So what does our transformation look like? Well, x equals r cos theta, y equals r sine theta, and z just equals z. That's what our transformation looks like. And what does a kind of rectangular region here look like? Well, a rectangular region would look something like r goes from, say, 0 to r naught, theta goes from, say, 0 to 2 pi, and z goes from, let's say, a to b. Maybe something like this. And let me just come over here to the side. So we'll go from z equals a to z equals b. And I see that theta is going from 0 to 2 pi. So we're going all the way around the xy direction. And r is going from 0 to r naught. So we have just kind of a cylinder that we're dealing with here. And I guess maybe to make the perspective look a little better, I will make that a dotted line in the back there. So a cylindrical coordinate rectangle is essentially a cylinder, right? If we set up r, theta, and z's bounds to be completely independent of one another, we get something like this, something like a cylinder. Now, I suppose, I mean, we could let r go from, say, r naught to r1, and theta to go from theta naught to theta 1, but then we're just getting kind of a slice out of a cylinder. So we'd just be getting some kind of three-dimensional, kind of almost cuboid looking thing, but it would be a chunk of a cylinder instead. But if we start r and theta at 0, then we get something, and if we let theta go all the way to 2 pi, we get something that is a little more recognizable as a cylinder. Okay, so after all of this, what can we say? Well, again, we have our transformations, just the same polar transformations, and then we just let z equal z. Again, we're only really changing the way we describe the point in the horizontal plane, the xy plane, and we're still just going up z units vertically. Our triple integral can be written in rectangular coordinates, or our dv, well, dv is really just dA times dz, right? But dA we found before was just r dr d theta. I'm having trouble selecting it, but you get the point. So we just have dv is just dA times dz, so r dr d theta times dz. Okay, so let's use this idea to compute a couple of integrals. So for example, one, we want to compute the integral of the function f of x, y, z equals z over this region D. D is the three-dimensional space where x squared plus y squared less than or equal to 4. So that's a cylinder. And where z is between 0 and y. Now keep in mind, again, up here we were thinking of double integrals. Down here we're thinking of triple integrals. So we're thinking of the three-dimensional region we're going to draw as the region of integration. And then we have a function that maybe represents something like temperature at each point in that three-dimensional domain. And that's what we're adding up. So what we're going to draw out here is just the region of integration. And then the integrand is just going to go inside of that integral. Okay, so let's try to get a picture of this. So x squared plus y squared less than or equal to 4. Note that we've made it very clear that we're talking about a three-dimensional region here. So x squared plus y squared less than or equal to 4 is in the xy plane a circle of radius 4, or I suppose a disk of radius 4. But then z is free, so we just move that disk up and down. This is a cylinder of radius 2. I think I might have said radius 4 just a minute ago. I should have said radius 2. And of course, this cylinder extends up and down as far as we want, but we're only going to draw a part of it because that's what we're interested in here. And then we're letting z go from 0 to y. So z equals 0 is the xy plane. So we want to be above the xy plane, the domain over which we're integrating. And we want to be below z equals y. Well, z equals y doesn't depend on x. So as we move x, it's just going to kind of copy whatever tracing we have in the yz plane. And of course, z equals y is just the 45-degree line in the yz plane. So we just have this plane. It's a little hard for me to draw from this perspective. Let me kind of draw it a little bit differently here. We have this plane. It's a 45-degree plane. It maybe doesn't look so great the way I've drawn it, but I didn't want it to be like running right along the x-axis there so much. So I have this 45-degree plane. This is inclined 45 degrees from y, so use your imagination a little bit there. And it's intersecting this cylinder. So what does this region look like if we maybe rotate it a little bit? It looks something like this. Like if you imagine a bunch of letter Ds that were shrinking and kind of get stacked on top of one another, making this kind of pyramid-like looking thing, where one side is kind of the curve that's the outside of the cylinder, and the other side is a flat plane that we slice through. So this is the region that we're integrating over. And we see that in the XY plane, well, X goes from -2 to 2, and we're integrating over this region up here. So that's the just looking straight down at that region. And then, of course, Z is going from, if I take a vertical cut here, so maybe looking something like this, Z is going from 0 to Y. Okay, so I see that kind of in the XY sense, in the horizontal plane, I want to describe this two-dimensional region somehow. And then my Z is going to go from 0 to Y. And I think it's pretty clear that cylindrical coordinates will work nicely here. Describing this XY region in essentially polar coordinates, that's essentially what we're doing with cylindrical coordinates. And that's going to work nicely to describe this piece of circle. So I see instead of X and Y, I want to describe it in terms of R going from 0 to 2 and theta going from 0 to pi. And here I got to be a little bit careful. Z goes from 0, but Z equals Y. Well, I don't want to be talking in terms of X, Y, and Z anymore. I want to be talking about R theta and Z. So I just substitute in Y equals R sine theta. Now keep in mind, I'm integrating a function over this region. F of X, Y, Z equals Z. And Z is one of our variables of interest, R theta and Z. So we'll just leave that alone. So my integral then is going to be integral theta equals 0 to pi. I see that Z's upper bound depends on both R and theta. So Z had better be the innermost integral. R goes from 0 to 2. And Z goes from 0 to R sine theta. My integrand is just Z. And then my little chunk of volume, my dV, is dz times dA from polar coordinates, or just R dz dr d theta. And again, I might be tempted to pull out the theta integral or something from all of this, but I have to be careful because that R sine theta in the upper bound of Z does mean that everything is also dependent on theta. So let's just take this step by step. This R can come out of the Z integral. And then I'm integrating Z between two bounds. Well, that's going to be a 1/2 Z squared between those two bounds. Or that's going to be a 1/2 times what ends up just being R squared sine squared theta. this minus 0 squared, just r squared sine squared theta, and then dr d theta. Now, if I look at this integral, I do have an integral where both of the bounds are independent. This is essentially a polar rectangle. Neither the bounds on theta nor on r depend on the other variable. And also my integrand, my function on the inside, is the product of a function of r times a function of theta. Well, this I can split apart now. Let me be a little careful here. I got my 1/2 factor. I got my sine squared theta. And then I need to make sure I get all of my r. So I need to get r cubed dr. Okay, so I've got a 1/2. Sine squared theta is going to be a 1/2 1 minus cos of 2 theta d theta. So that's just using a trig identity. We didn't do any integrating yet in the theta integral. I know this is a minus because if I plug in 0, I should get sine of 0 0, and I get 1 minus 1 is 0. So that's how I remember which one of those is plus or minus. And then for my r integral, I should get 1/4 r to the 4th from 0 to 2. Okay, so I guess I get 1/2 times 1/2 times 1/4 is 1/16 times 2 to the 4th is 16. So nicely enough, all of this goes away. And then I got to do this theta integral. I get theta minus 1/2 sine of 2 theta from 0 to pi. Now, of course, this at 0 is just 0 minus 0. And at pi, sine of 2 pi is 0. So this whole thing just gives me pi. Okay, so again, when we're going through the integration, we have to be a little bit careful not to jump the gun with splitting integrals apart or factoring things out. That's an easy mistake to make, is to forget about this upper bound here and just take for granted that, oh, theta goes from 0 to pi. We can always just make that a pi minus 0 and make that pi. And then at the end, you're going to end up somehow with an extra theta floating around, and you're going to think, wait, why did I should be getting something that's a number, that's a constant, and somehow I've still got thetas left. If you ever get to the end of a double or triple integral and you still have some variables left, see if you did something like that. Go and look back and say, did I pull out an integral when I really ought not to have done that? It's an easy mistake to make. Okay, sometimes the formatting looks great whenever I have it in a slightly different window, and then it looks a little goofy when I change the window size. So there we go. Let's look at this next example. Find the volume of the solid region cut from the ball x squared plus y squared plus z squared less than or equal to 4 by the cylinder x squared plus y squared equals 2y in the first octant. Okay, so let's draw a picture to try to get a handle on what's going on here. Okay, so I have a ball, a filled in sphere of radius 2. So like that. I think I might actually take out that horizontal curve because I think that's going to make it look a little crowded in here. And then I have a cylinder. Well, let's see, what is this cylinder? This is x squared plus y squared minus 2y and I'll make this a plus 1 equals 1, or x squared plus y minus 1 squared equals 1. In the xy plane, this is a circle of radius 1, centered at x equals 0, y equals 1. It's a circle like that. So I have what amounts to a circle kind of like this that's cutting down through the sphere. So in the xy plane, it's going to cut out a whole chunk of the sphere. But as we kind of cut down through, it's going to trace out something that looks a little bit like this, and something similar on the bottom side. So we're just kind of boring a hole of radius 1 through kind of the edge of this sphere. So we end up with a region that looks kind of like this. And maybe I'll make the inside a different color. Green actually looks pretty close to blue, at least to my eye anyway. So maybe the inside will be red. So that's kind of the shape that we have. Here I've kind of, I guess, drawn a like hollow shell of the solid, but we're thinking of this as a three-dimensional solid. And we want to find its volume. So I note that z goes from, well, it's going to go from what? Pretty clearly, we're working in cylindrical coordinates because our region's a cylinder and everything works pretty nicely with cylindrical coordinates. But I see that I have z squared. Well, the boundary is z squared equals 4 minus, but x squared plus y squared is r squared, right? Just the same thing from polar coordinates for the same reason. X squared plus y squared is r squared. So z squared is 4 minus r squared, or z goes from minus root 4 minus r squared to plus root 4 minus r squared. So that's one component of my bounds of integration. And then I can look at my polar curve. Now remember, I only want the first octant, so I really only want half of this solid here that I drew, I suppose. So I don't want this piece. I do want that piece. I see that x squared plus y squared. So the x term isn't 0 in this case. I'm not sure what you're asking there. Can you rephrase that or clarify that?
I'm talking about like the ordered pair. So like the order pair you just put down. Since we're working in the first octant, you mentioned in one of the earlier problems that it was 0 to something, but maybe it's not in this case.
Yeah, so I mean, x would be like 0 to 2, and y would be, whatever whatever you would get from, it'd be something like 1 plus or minus what? It would be 1 plus or minus square root of 1 minus x squared. So not the nicest thing to work with in rectangular coordinates, but we would get something like y is 1 minus root 1 minus x squared, so 1 plus root 1 minus x squared. So we could describe it in rectangular coordinates this way, and x would be just going from 0 out to 2, not from minus 2 to 2. But we're going to describe it in cylindrical coordinates because it's going to be quite a bit nicer. Does that answer your question? Okay. Um, yeah, so let's take a look at, so we looked at a nicer way to envision this in rectangular coordinates so we could get the circle drawn out and get things situated, get our picture drawn and everything. But in polar coordinates, well, x squared plus y squared is r squared, and y is r sine theta. Since r is not always 0, it just goes away, and we get r equals 2 sine theta. So for a given angle theta, r is going to go from 0 out to 2 sine theta. And then theta is going to sweep out from 0 to pi over 2 to just stay in terms of the xy plane in the first quadrant. And that will keep us in this first octant up here. And I do have to be careful. First octant, I should be starting at, I think I made the same error last time. I should be starting at 0 here to stay in the first octant, to stay above z equals 0 as well. That might have been what you were asking about, is this lower bound on z should be 0, and then the upper bound at square root. Now I'm just looking for the volume. So I'm just looking to do a triple integral over this region dv. Or that's going to be integral theta goes from 0 to pi over 2. R depends on theta and z depends on r. So the z integral has to be inside the r integral, and the r integral has to be inside the theta integral. Okay, so we get that, and then we just get dv, which is r dz dr d theta. Again, I don't want to get too ambitious here and try to pull out the theta integral, because that 2 sine theta in the top of the r integral is keeping us from doing that. The z integral has r in its bound as well, so we're just going to do this as an iterated integral. We can pull the r out front. And then we're just integrating dz between these two bounds, which just gives me root 4 minus r squared dr d theta. And again, I still can't pull out the theta integral because of this 2 sine theta at the top there. So I'll keep going as an iterated integral. And here I see that this is going to be just a basic substitution now, thanks to this factor of r. That's the other thing that cylindrical coordinates is going to help us with here, not only describing this region a little more easily than doing all of this stuff, but also helping us with the integrand, helping us to describe that, or to get an integrand that we can do just by basic substitution. I mean, it wouldn't be the end of the world to do maybe a trig substitution or something, but this is even easier. So integrating 4 minus r squared to the 1/2 is going to look more or less like 4 minus r squared to the 3/2. I need a 2/3. Now, if I differentiate this, I get 3/2 times 2/3, that goes away. 4 minus r squared to the 1/2, that's this bit, times negative 2r. So I need to get rid of that negative 2. I need a negative 1/2 to fix my constant. And then r goes from 0 to 2 sine theta. And I'm integrating all of that d theta. Okay, so what do I get here then? I guess I can make this integral theta equals pi over 2 to 0. I use the minus sign to flip the bounds of integration. The 2's cancel, and I get a 1/3 times, well, 4 minus 2 sine theta squared. That's 4 minus 4 sine squared theta. And that is all to the 3/2 power. So yeah, 4 times 1 minus sine squared theta to the 3/2 minus, when I plug in r equals 0, be careful here. It's easy to get a little careless and just think that the second part is 0, but it's really 4 minus 0 to the 3/2. And I guess I need curly braces to go around all of this. I see a 4 to the 3/2 comes out. That's square root of 4 cubed. That's 2 cubed is 8. Comes out of everything. And then what do I have? I have a 1 minus sine squared theta to the 3/2. Well, 1 minus sine squared theta is cos squared theta. Square root of that is cos theta. Cubed is cos cubed theta. And then I just have a minus 1 left over. So the 4 to the 3/2, I factored out. That was just the 8. And then the 1 minus sine squared theta to the 3/2 turned into a cos theta cubed. And then the 1 that was left over from here just came out as a 1. All right, and then we have what? 8/3 times, what's the integral of cos cube theta d theta? Well, this is the integral of uh, cos squared theta cos theta d theta, which is the integral of 1 minus sine squared theta cos theta d theta, just with Pythagorean identity. And then we use u equals sine theta. This gives me the integral of 1 minus u squared du. Derivative of sine is just regular cosine, so no sign changes or anything here. This is u minus 1/3 u cubed, where u is sine theta. So that is what cos cubed theta integrates to. And then, of course, minus theta from the minus 1, going from pi over 2 up to 0. Again, we switch those bounds just to get rid of the negative, because if I pop the negative all the way out front, I'd probably forget it at some point. It's easier in my mind to switch the bounds, because that's something you're less likely to misread going from one line to the next. It's easy to, miss an extra little negative in front like that. Okay, so at theta equals 0, at theta equals 0, this gives me 0. I feel like I'm off by a negative somewhere anyway, even though I was careful not to, or I thought I was being careful not to be. Oh no, okay, yeah, it is looking right. Okay. So at 0, I get all of the sine of 0 is 0 and theta is 0, and then minus this thing evaluated at pi over 2. So sine of pi over 2 is 1 minus 1/3, and then minus pi over 2. Or this is 8/3 times pi over 2 minus 2/3. Yeah. Okay, any questions on this one? Okay, then let's move on to spherical coordinates. So moving on to spherical coordinates, this is going to be related in a way to polar coordinates and cylindrical coordinates, but it's not going to be as closely tied, at least at first glance, to those coordinate systems. So what's the idea of spherical coordinates? Again, we have some point x, y, z. It's z units above some point x, y in the xy plane. And I would like to describe this point in terms of radial distance, but really kind of more fundamentally in 3 dimensions in terms of radial distance. In other words, I want to start at the 3-dimensional origin, point you in some 3-dimensional direction, and then tell you just walk straight in that direction. I don't want to tell you walk straight in this 2-dimensional XY plane and then go up, but I want you to walk straight towards the point from the origin. We're going to call this radial distance rho. This like kind of curly P is rho, the Greek letter R. And we're just using that so that we don't get it confused with the radial distance R that we tend to use in polar and cylindrical coordinates. Not that it would be, say, wrong in some way to use R here, but it's just that it's kind of playing a different role than we've seen it playing before, so we're going to call it something different. There is a bit of inconsistency in how different fields use or name these different things. So, just be aware of that. If you're in a physics class or something like that, you might see you might see this thing called R instead of rho, but it's just, just the way that we choose to label things. Now, what do I have to tell you to point you in the right direction? Well, I have to tell you maybe in the vertical plane, how far should you rotate around? And then kind of like, what's your angle of elevation once you're in that direction? So I still am interested in theta as well as r from my polar coordinates. I'm going to tell you start at the origin, start looking out horizontally along the x-axis, and then rotate towards the positive y-axis, theta degrees or radians, and that'll get you kind of pointed in the correct horizontal direction. And then I'm going to tell you look up, let's say, a bit. It turns out that it's a little easier to describe things saying look straight up and then look so many degrees down. So we're going to have kind of an angle of decline, or kind of the opposite, I suppose, of an angle of elevation. The angle from the z-axis, from the positive z-axis, we're going to call that angle phi. So this letter is phi, or sometimes people call it phi. It's the Greek letter ph. And it's going to represent the angle between this radial line labeled rho here and the positive z-axis. So if I tell you start at the origin, look horizontally along the positive x-axis, rotate theta degrees or radians towards the positive y-axis, and then when you're looking in that direction, look straight up and then come down phi degrees or radians. And now you're looking in a certain direction, in 3-dimensional space, then go in that direction, rho units. That's another way to describe x, y, z. I could describe it in terms of rho, theta, and phi. Theta and phi kind of set the direction in 3-dimensional space, and then rho tells you how far to go in that direction. Now, something that I do notice is if I think of my little polar coordinate graph here, if I look at the red line labeled rho and the green line labeled r, and then my kind of dotted line, my dotted vertical line representing z units above the point xy or the point r theta, I can think of that. So here I have z. I can think of that just as a right triangle where rho is the hypotenuse, r is the base, and z is the vertical leg. So I see that rho squared is r squared plus z squared. I also notice that if I kind of imagine my rho line here having an angle phi from the vertical axis z, well, that puts an angle phi, didn't draw that phi very well, puts an angle phi up here. These two lines are parallel, and we have a straight line intersecting them, so those angles are the same. And I see I can describe z, r, and rho in terms of, or z and r in terms of rho and phi. So I see that what sine phi equals r over rho says that r equals rho sine phi. And I also can describe z. I see that cos phi is z over rho. So z is rho cos phi. So I now know how to switch z into rho and phi. What about x and y? Well, x from polar coordinates or cylindrical coordinates I know is r cos theta. So that's r cos theta, not rho. But I know how r transfers over to rho and phi. R is just rho sine phi. I guess I'll give this a squiggly outline. And then likewise, I know for y as well, from polar or cylindrical, I know that y equals r sine theta. But again, I know that r is rho sine phi. I also know that r squared equals x squared plus y squared. The polar r squared is x squared plus y squared. So that tells me that rho squared is x squared plus y squared from the r squared plus z squared. And I mean, that makes perfect sense. Rho is the distance from the origin to xyz, right? I mean, but we can see directly from these bits over here that we get that out. Okay, so I have a good bit of material to work with now. I know how to translate xyz back and forth between rho, theta, and phi. And I have maybe a couple of helpful identities here. Now let's look at a little chunk of volume and try to understand what's happening with the chunk of volume, a little dv. What does dv look like? We suspect it's not going to just look like d rho, d theta, d phi. It's probably going to have some other stuff in it. Just like with cylindrical coordinates, up here, dv didn't look just like the r d theta dz. It had this extra little r coming into play. So do we just get a rho down here? Do we get something else? Let's take a look. All right, so let's suppose that up here we have, I'm going to try to draw this pretty reasonably well. So we have this little chunk of volume here, or let me call it delta V. I get this chunk of volume by letting theta go from some theta, or sorry, phi go from some phi to another, letting it go along a change in angle of delta phi. I'm letting theta sweep out a delta theta. So this piece here is related to delta theta. This piece here is related to delta phi. And then I'm letting my radial distance coming out this way change by delta rho. So when I allow my radial distance to change from, say, rho to rho plus delta rho, letting my theta angle change from theta to theta plus delta theta, and my phi angle change from phi to phi plus delta phi, how does that affect my volume here? Well, really what I want is kind of my three sides lengths. Well, if I let rho go from rho to rho plus delta rho, well, this side length here is just delta rho. Okay, nothing big there. When I let theta go from theta to theta plus delta theta, that sweeps out an angle delta theta. But remember, when I sweep out an angle delta theta, this side length here looks like r delta theta. And here I'm using r that's this r. So not rho, but r, the kind of polar r. And then I'll do this in a different color just so that it makes it a little easier to see. What about this side length here? And I've got a lot of arrows and things, so hopefully the colors make it clear what's pointing to what. Well, this side length here, this is phi sweeping out an angle delta phi. So phi is sweeping out an angle delta phi, but that's out there at a radial distance of rho. So that side length looks like rho delta phi. And we approximate this volume as though it were a cuboid, which I didn't draw particularly well there, but we approximate it as a cuboid, where for small delta rho, delta phi, and delta theta, the little chunk of volume that we're talking about here is delta rho, approximately, should say approximately, times rho delta phi times r delta theta. So I expect my little, my dv to look like r times rho, d rho, d theta, d phi. And I'm almost there. So I'm saying r times rho, but remember in spherical coordinates, we don't want r sticking around. We want to describe everything in terms of rho, theta, and phi. So r in this case is rho sine phi. But we can really see that we get kind of two polar coordinate type pieces out of here. That's where this comes from, this r rho. But then r is just rho sine phi times another rho, d rho, d theta, d phi. So our little chunk dv turns into rho squared sine phi, d rho, d theta, d phi. And this is really just r, just kind of one radial distance times the other radial distance that have come into play. So that's really behind the scenes. It's much more sensible than if you look at this and you say, wait, where the heck did rho squared sine phi come from? Well, it's just r times rho. It's just the xy plane radial distance times the three-dimensional radial distance. So it's essentially coming from the same thing, just two different perspectives. And then we're switching everything into the rho theta phi world. So that's where we get the r equals rho sine phi. It makes this look, a lot different than just r times rho. So spherical coordinates, we do our triple integral, making this change of variables for x, y, and z. And importantly, we need to remember to tack on a rho squared sine phi as part of the dv. So that rho squared sine phi will be there regardless of what integrand you're integrating, regardless of what domain you're integrating over. That's part of the dv here. This dv is this rho squared sine phi, d rho, d phi, d theta. Okay. So now let's look at a couple examples. Let's find the volume of the solid region below the upper half of the sphere, x squared plus y squared plus z squared equals 9, and above the cone, z squared equals x squared plus y squared. So I see I've got a sphere of radius 3. And then I have a cone, z squared equals x squared plus y squared is like a 45-degree cone, right? If I let x be 0, I see z squared is y squared, z is plus or minus y. So this cone looks kind of like that. So I'm looking for this kind of like ice cream cone shape, like a cone on the bottom and then a lump on the top, a spherical top to it. So in say the y z plane, I see I have something like this. This is radius 3. And this angle is pi over 4. And then in the xy plane, I see that I'm just integrating over some circle. So I see that theta, which describes kind of how far around do I turn in the xy plane, goes from 0 to 2 pi. I see phi, if I look at this above the cone, phi equals 0 is when I'm right along the z-axis, and then I'm letting phi increase until it gets out to pi over 4. And then, of course, I'm letting my radial distance go from 0 to 3. So this kind of wedge of a sphere, so to speak, this is actually a rectangular region in a sense in spherical coordinates. This wedge of a sphere is the type of region in spherical coordinates where r, theta, and phi all operate completely independent of one another. This is kind of like a rectangular or like a cubic region in a sense, but from the perspective of spherical coordinates. And again, if I just want to find the volume, I'm just integrating dv, or I can integrate theta going from 0 to 2 pi, b going from 0 to pi over 4, r going from 0 to 3. I called it r. I should be more careful. This is rho, of course. Pretending I'm a physicist for a minute there, I suppose. On one hand, it is a little inconvenient to have to remember to switch between r and rho, and it's just a notational, detail, so it's not really wrong if you don't. But on the other hand, it makes things like our discussion up here so much easier when we can keep straight which radial distance we're talking about. So it does have its uses, even though sometimes it's a bit of a pain. Now, we do have to be careful here. We're not just d rho, d theta, d phi, but rho squared sine phi, d rho, d phi, d theta. Now, I do notice that neither the integrand nor any of the bounds of integration depend on theta. So the theta integral is just going to give me 2 pi. I also note that neither the bounds on phi or rho depend on the other variable, and the integrand is the product of some stuff with rho times some stuff with phi. So it's going to be integral phi equals 0 to pi over 4 sine phi d phi times integral rho equals 0 to 3 rho squared d rho. So I can split those two apart. And if I integrate sine phi, I get negative cos phi from 0 to pi over 4. And if I integrate rho squared, I get 1/3 rho cubed from 0 to 3. This gives me 2 pi times, and I can switch my bounds of integration and get rid of the negative. So I get cos of 0 is 1, minus cos of pi over 4 is root 2 over 2. Pi over 4, 45 degrees, that's where cosine and sine are equal. And then times 1/3 times 3 cubed minus 0. Or this gives me what? 3 squared is 9 times 2 pi is 18 pi times 1 minus root 2 over 2. And that's my answer. Even though my region was a quote rectangular region, this still wasn't, a completely trivial integral to do because I have this little extra contribution in my dv. So I did have to take care to remember to put that in there and to actually do those integrals for rho and phi. Again, easy to forget to leave that out if you forgot about this, and then just kind of multiplied by 2 pi times pi over 4 times 3, you wouldn't get the right answer. So important that we do have that in there. Okay, example 2. Let's integrate the function f of x, y, z equals x squared plus y squared. So z equals x squared plus y squared, that's a paraboloid opening upwards. Integrate that over the sphere of radius 4, centered at the origin. Okay, so I'm going to draw my sphere of radius 4. Oh, missed my positive x-axis there, but 4 on this side as well. So I have a sphere of radius 4, and I'm integrating a function over this domain or region of integration. So this is something like say a temperature at each point in this sphere, and I want to add it up. Well, for this sphere, I noticed that theta, I'm going all the way around. I noticed that rho, my radial distance, goes from 0 to the radius of 4. And here I've got to be really careful. I might be tempted to say, okay, phi, well, phi also goes all the way around, so maybe phi goes from 0 to 2 pi. But we really have to think about, oops, went a little too far there. We really have to think about, if I want to trace out this 3D shape, how am I going to do that? Well, if theta is going from 0 to 2 pi, it's kind of taking something and wrapping it all the way around. It's revolving it all the way around the z-axis. So to make a sphere, I don't want to revolve a circle completely around the z-axis like this, 2 pi radians. If I did that, I would kind of get double the sphere, right? Like this right half would trace out a whole sphere as it goes around, but also the left half would trace out a whole second sphere as it goes all the way around. So what's my kind of two-dimensional in, let's say X and Z, what's my two-dimensional figure that I want to rotate around 2 pi to get a sphere? Well, I kind of think of it like, did you ever buy one of those like party decorations where it comes kind of folded up and you open it up and it turns into like a little ball kind of thing? Well, when you get one of those, let me erase back to here. Oh, went a little too far again. When you get one of those, it looks just like a half circle like this. So it's kind of all folded in on itself like a half circle. And then if you rotate this 360 degrees, 2 pi radians all the way around the z-axis, that's going to trace out the entire sphere. So I actually don't want phi to go from 0 to 2 pi. I don't want it to go all the way around. I want it to go from remember phi is this angle here, from 0 along the positive z-axis down to pi along the negative z-axis. It's going to trace out that half circle. And then when I take that half circle and rotate it around 360 degrees or 2 pi radians around the z-axis, that traces out my entire sphere. So we have to be a little careful with this, right? We can't really look at theta and phi completely independently. We have to imagine, typically how I think of it is, what region in rho and phi do I want to start with so that when I rotate it along theta, whatever the bounds on theta are, I get the solid that I'm interested in, or the three-dimensional region I'm interested in. And here, that upper bound on phi ends up being pi. Okay, but now that we do have this, we're integrating this integrand over this region. Again, of course, a sphere is a, quote, rectangular region in spherical coordinates, so that works pretty nicely. And then I want to integrate my integrand, which I'll come back to in a second here. And then I have my dv, remember, which is rho squared sine phi times everything. So this all is dv. And then what's x squared plus y squared? Well, x squared plus y squared, coming all the way back up to here, it's r squared, not rho squared, but r squared. But r is rho sine phi. So that's rho squared sine squared phi. So I can use my knowledge of polar coordinates to kind of help me out here and write this a little more simply. I could also have gotten it from here, right? X squared plus y squared. I factor out a rho squared sine phi and get cos squared plus sine squared theta. I could have done that as well, but I think a little more work than just using this r equals rho sine phi directly. So we need a rho squared sine squared phi as the integrand. This is the function that we're integrating. This is like our temperature or whatever, our number that's the output of the function at each point in this 3D domain. Okay, now if I look at my inner integrals for phi and rho, neither the bounds nor the integrand depends on theta. So this theta going from 0 to 2 pi can just turn into a 2 pi. I also see that for theta and rho, for those integrals, the bounds don't depend on the other one. And my integrand, everything can break apart as function of rho times function of phi. So I can break these two integrals apart. Phi goes from 0 to pi, and I get a sine cubed phi d phi. And then rho integrates from 0 to 4, rho to the fourth, d rho. So this gives me a 2 pi times something that I'll come back to in a second here, times 1/5 rho to the fifth, rho going from 0 to 4. Then I need to integrate sine cubed of phi d phi. Let me just come over here and do that as some scratch work over here. And I know that I have an even number of powers of sine, so I break one of them off to use as a du. And if I let u be cos phi, du is negative sine phi, so this is going to give me integral of u squared minus 1. I'll use that negative just to switch the order of the 1 minus u squared to a u squared minus 1. This gives me u cubed over 3 minus u. And I said u was cos phi. So I think this gives me 1/3 cos cubed phi minus cos phi. And phi going from 0 to pi. Let me just double check that in my notes. I did that kind of quickly and a little sloppily. Make sure that I got that right. That does look right. Okay. I didn't drop a negative anywhere or something. All right, so I end up with 2 pi times 1/3. So cos of pi is -1. So that's -1/3 plus 1. And then cos of 0 is 1. So that's a minus 1/3. And then a minus is a plus. cos of 0 is 1. And then over here I get times 1/5. 4 to the 5th is 2 to the 10th. I'll write it that way so I can combine it with the other 2 in front. And then, of course, minus 0. So I get, what, 2 to the 11th pi over 5. That takes care of these bits, times 2 minus 2/3. Well, that is, what, 6/3 minus 2/3 is 4/3. So that's an over 15. And then 4 times 2 to the 11th is 2 to the 13th. So that's what our answer is, 2 to the 13th over 15 times pi. Any questions on this one? Okay, and then our last problem for today. So example 3, integrate the function f of xyz equals z over the volume lying below the upper half of the sphere, x squared plus y squared plus z squared equals r squared, big R squared for some big R. And above the cone, z squared equals x squared plus y squared. So this region is going to be kind of like an ice cream cone looking thing, like in example 1, but instead of just finding its volume, we're looking to integrate an integrand over that region. So just like above, we have an upper half sphere of radius big R. And then we have this kind of 45-degree cone. Z squared equals x squared plus y squared. In my YZ plane, I see that I have this 45-degree line and this little circular segment up top. So phi goes from 0 to pi over 4. OneNote loves trying to correct my 4s to 9s. Close off that little top piece. I should just start drawing my 4s like this, but I've never drawn 4 like that, and it just, I can't switch at this point. I see that my radius, regardless of what phi is, my radius goes from 0 out to radius big R. Some constant, but arbitrary. And then I see that in my XY plane, I'm going all the way around. I see that theta goes from 0 to 2 pi. And importantly, I want to integrate this integrand over this region. So this description of rho, theta, and phi gives me the region. I need to make sure that I have my dv right with that rho squared sine phi. And I also need to make sure that I put my integrand in there. Lots of little details to remember here. So I'm going to integrate theta going from 0 to 2 pi. Phi going from 0 to pi over 4. And rho going from 0 to the constant big R. I'm integrating my integrand. I'll just write it as z for the time being, but we'll think about that in a second. And then I have rho squared sine phi, d rho, d phi, d theta. And then, of course, remember that this is my angle phi here, and this is rho, and this is z. So I have cos phi equals z over rho Z equals rho cos phi. I put my Z in there as a placeholder because I wanted to make sure I didn't forget to stick it in there as the integrand. There's just a lot else going on. But now I see that I'll replace it with a rho cos phi. This is my Z, the thing that I'm interested in integrating, my something like temperature at each point in this region. I do notice that for my 3 bounds of integration, this is a rectangular region in spherical coordinates. So the bounds, none of them depend on one another. I notice that my integrand can be separated into a function of rho times function of phi. My theta can come all the way out. So this gives me 2 pi contribution from the theta integral. My phi integral, I get integral of cos phi times sine phi d phi. And then my rho integral, rho goes from 0 to big R of rho cubed d rho. I see that I can steal this 2 and put it inside here, and 2 cos phi sine phi, 2 sine phi cos phi is sine of 2 phi. So I have a pi, sine of 2 phi integrates to negative cos of 2 phi times 1/2, going from 0 to pi over 4. And my rho integrates to 1/4 rho to the 4th from 0 to r. Or this is pi over 2 times, well, this negative just switches the bounds. So that's cos of 0 is 1 minus cos of 2 times pi over 4, cos of pi over 2, that is 0. Cos of pi over 2, that's the x coordinate when we are straight vertical along the y-axis, that's 0. And then this gives me big R to the 4th over 4. And then minus 0. So when all is said and done, I get pi times big R to the 4th over 8 as my integral, integrating Z over this region. Any questions on anything we've done today? Okay, so I think these are, in some sense, a pretty straightforward generalization of things like polar coordinates and double integrals and polar coordinates. But in another sense, there are, just some little technical details to really keep in mind and be careful about. But I think if you, view it from the standpoint of polar coordinates, that helps a lot. That helps to remember the formulas as well and to see where things come from, like particularly the rho squared sine phi seems to come out of nowhere. But if you see that it's just r times rho, that makes a little more sense. Yeah, so, part of the challenge also is if you're just given a random integral, recognizing that, okay, this is going to work nicely, say, as a transformation to spherical coordinates or into cylindrical, and that's going to depend somewhat on the integrand as well as the domain. But I think some of that just comes with practice and pattern recognition and so on. But also, looking for things like, will this domain be much nicer to represent in some kind of polar way than in a more rectangular way. Oh yeah, in the last problem, R was just an arbitrary value here. So the point is, it doesn't really matter the radius of the sphere, right? This same idea works, and we can see that, if we were thinking of this as something like, say, temperature, maybe something like the amount of heat or so, something along those lines. scales like r to the fourth as the sphere gets bigger. So that's really what it tells us, is that as our sphere gets bigger, as the radial distance of the sphere gets bigger, the volume of the sphere scales like r cubed, but the heat or something like that scales like r to the fourth. Yeah. So yeah, for this problem, don't read more into it than it's just an example. But yeah, you wouldn't necessarily like solve for big R or something like that. We're just saying for a general sphere of radius big R. There's kind of a funny the physicist Richard Feynman did a series of lectures. You can find them on YouTube. I forget, it was at a certain college. It might have been at Caltech, and he was doing a series of lectures on physics, obviously, kind of just talking through some big ideas in physics. One kind of big idea per lecture, more or less. And one of the lectures, he was saying, he was making a joke about the way physicists versus mathematicians look at things, and he says, so I went to this mathematician and said, hey, I got this problem, there's a physics problem, but I can't figure out how to solve the integral or whatever he was trying to solve, and give it to the mathematician. Hey, can you solve this for me? And the mathematician comes back a couple days later, and here, I solved it for you. Wait, what is this n? Says, oh, that's the dimensions. It's like, what do you mean? It's like, well, that's the solution in n dimensions. Says, well, but we live in 3 dimensions. I wanted the answer in 3 dimensions. He says, well, just plug in n equals 3. So mathematicians, there's a saying that one of the professors at Pitt, when I was in grad school, I never actually had him for a class, but it was a famous saying of his that he says, be wise, generalize. So mathematicians like to do things like put in arbitrary constants like r squared, and and then you solve the whole thing. And if you're interested in the sphere of radius 2, you just put in big R equals 2. But yeah, no more importance for why there's a big R here than just that. We're just solving it for some sphere of arbitrary radius. Yeah, but good question though. Okay, so yeah, and part of this, just like in Calc 2, when you're trying to decide, I look at an integral, what's the best integration technique to use? Should I do integration by parts or substitution or trig sub? A little bit of it is just doing several of them and getting some pattern recognition down. And I think the same thing goes here. Should I use rectangular coordinates and just kind of tough it out? Maybe it's a little bit annoying to do. Or will it be a lot easier if I switch to cylindrical or spherical? Maybe the domain gets easier, but the integrand gets harder. Is it worth that trade-off? Maybe not. So, and some of it is just a matter of, sometimes you take the wrong route and you go this way and you say, oh, I got halfway through the problem and it's becoming super messy. Let me back up and see if I go a different route, does the problem yield more easily? Okay, so as I mentioned before, the surface area supplement is up and available, and change of variables I'll have available tomorrow, and that'll wrap up chapter 15. And then we'll move into chapter 16 on vector calculus. So I do have a couple of resources listed on vector calc if you're interested. I actually have the books in the other room, so I can't hold them up to show you, but one of them is more of a mathy book. It's by a guy named Shea, Schey, called Div Grad Curl and all that. And this is on the syllabus as well as on Blackboard if you want the details. It's a red book. And if you get the most updated edition, I think he switched some notation around to make it more consistent with either the math folks or the physics folks, I forget. But if you want, a little more in-depth guide to vector calculus, that can be helpful, a helpful resource. If you want to see how the stuff we're going to cover in chapter 16, which seems very abstract and like we're just making all this crazy stuff up, this is never going to be used. If you want to see how it's actually used, there's a book, I think it's by Daniel Fleisch, called Student's Guide to Maxwell's Equations. And it actually walks through each of Maxwell's equations and shows how these different ideas of divergence, gradient, curl, Stokes theorem, and so on, shows how all of these are used in the context of Maxwell's equations, which model electromagnetism and light and electricity and those kinds of things. So a very fundamental idea in physics. So either one of those, they're both fairly thin paperbacks. They're fairly cheap relative to what academic books cost. You can find them used, I'm sure. So if you want an extra resource, those are good resources. Otherwise, you can stick with Stewart, and that's just fine. All right. I will see you all next week. Enjoy the 4th and enjoy your weekend.